Okay, so before we get into the, so as I said, we'll use the previous year's test as revision material. Are there any topics that you want to cover instead? Any tutorial problems that you want to go over? So anyway, you can think about that and tell me. So on Monday, we can have, sorry, not Monday, Tuesday, right? We can talk about that further. Okay. So here in this test, the first problem, so we are given an elementary reaction here. And so the rate expression is, of course, the concentration of each of the species raised to the stoichiometric coefficient. So this is KCA times CB cubed. So CA times CB cubed. So clearly it's that one. Then this one is looking at the relative reaction rates. So if we take the basis as being RA, we can see RA, both A and B are disappearing in the reaction, so they should have the same sign. So let's just check sign. So this one is wrong, right? We can't have RA being equal to minus something times RB. So it's we can eliminate this answer. And then if we look at the first one, A is consumed at half the rate that C is produced. So that's a statement that corresponds to that. And of course, we can use the formula that tells us nu A over, RA over nu A equals RC over nu C. So if you use that formula where nu A is -1 and nu C is 2, then we get that that answer. So that's the answer for that one. And then here we have a batch reactor charged with 50 moles of A and a stoichiometric amount of B. So that means if we have 50 moles of A, we must have 150 moles of B. And then after 1 hour, 10 moles remain. So 40 moles of A has reacted. And then we can see here, if 40 moles of A reacts, 80 moles of C will form. So the amount of C is 80. That one is correct. If we check for B, we know that if 40 moles of A has reacted, then 120 moles of B has also reacted. And so remaining will be 30 moles of B. So it's not A and it's not B, and then we know it's not C. So that's the answer for this one. So these are simple stoichiometry type questions. In terms of at equilibrium here, we can see that at equilibrium, A will equal 3 times the rate at which, B will equal 3 times the rate at which A is consumed. So that's true. And also the amount of C formed will be twice the amount of A. So it's not this one. It's also not generally true that RA is 0. So RA is consumed and it can be steadily consumed. So it's not equal to 0. RA is not equal to 2 times RC because A is consumed and C is produced. So that one is wrong. So the only one that makes sense is D. Okay, and then here, when we develop the equation, the flow, let's see, so for what reactor, the flow, to develop the batch reactor balance, okay? So yes, it's true, in the batch case, F equals 0, but we know it's not at steady state. So the batch reactor is not typically at steady state. And then in terms of this one, the flow is 0 and the reactor is perfectly mixed. It can be, right? The batch reactor, we always talk about it as if it's perfectly mixed. It's not necessarily, but anyway, most of the time we say it's perfectly mixed. So this could be true. Part C says it's at steady state. We know it's a batch reactor, not at steady state, so we can eliminate this one. And then the inlet flow is balanced with the exit. There's no flow in the batch reactor, so we can eliminate this. So the only one that can make some sense is this one. For the CSTR, flow terms are 0. We know it's not 0, and it can be at steady state. But this first part is not generally true. RA is a volume constant. Yes, it is a volume constant because it's perfectly mixed. So it is a volume constant. And it says here only at steady state. It's not the case that RA has to be constant only at steady state, right? This RA being a volume constant is a spatial statement. It states that the rate is the same at all points in the reactor. It doesn't have to be steady for that to happen. Even if it's unsteady, you can imagine the fluid flowing around and the flow rates changing. So you can imagine a case where it's not steady, but still that the mixing is high enough that the reaction rate is a volume constant. So it's not the case that it's a volume constant only at steady state. So this statement is not right. RA is a volume constant due to perfect mixing. So yes, we know that's true. And then RA is not a volume constant. So in the CSTR, where we define it to be perfectly mixed, it's not true that it's not a volume constant. So the only one that makes sense is this one. For the PFR, we apply steady state and find RA as a function of Z. I mean, we can. It's not necessarily true, but we can do that. So to develop a steady state, find RA. So it's unclear in this one why it's stated as a general one. So we don't really accept this one. We apply this balance at the differential scale in Z where RA is constant. So yeah, we do that. So there's nothing wrong with B. And then we let F equal 0 and use, we know F is not 0. There is flow through a PFR, so this doesn't make sense. And then we recognize RA is constant in Z. RA is not constant in Z. The rate will change with the Z position because the concentration is changing with Z. So that's not true. So the only one that makes sense is that one. Okay, CSTR means, first option, constantly stirred. So the reactor might be constantly stirred, but that's not the point of CSTR, right? Continuous stirred tank reactor, right? So I've just said the answer, that's continuous stirred tank reactor, right? This one says constantly stirred, this one says continuously stirred. So these two are all about the stirring. And CSTR is not about the stirring. Continuous stirred. So the continuous part here means the flow is continuous. So the C in CSTR means that we have a constant flow through that CSTR. It's not about, so these first two talk about the stirring constantly. So this doesn't mean it's constantly stirred. It means it's a continuous reactor. It always has flow through it. It's not necessarily steady flow either. It could be unsteady, but the point is it's continuous. You are always feeding and withdrawing from that reactor. The last one, continuously stirred thermal reactor. There's no such thing as thermal reactor. So the only one that makes sense is that one, continuous stirred tank reactor. CSTR is the worst possible use of the volume because, and we've said this many times, right? It's not true that there's only one steady state. You can have multiple steady states, as we saw. The flow rates don't have to be constant. And about it being easier to construct, that's not why it's so. In fact, a CSTR is the easiest one to construct. But because it's perfectly mixed, we are stuck to one concentration everywhere. And so that's why we get the lowest rate in the CSTR. When developing the energy balance, in the adiabatic case, we get this equation. So in the adiabatic case means Q equals 0, right? That's all that adiabatic means. Adiabatic doesn't even mean that the temperature is constant. So imagine a case where you have an exothermic reaction happening, and you don't try to cool down the reactor, you just let it react, then the temperature will rise even though you are not adding heat or removing heat. So the temperature can change even if it's adiabatic, which means only that we are not adding or removing heat. So we noticed originally there's no contribution to energy from the reaction because it's hidden behind Q dot. That's not true. That change in energy is not because of Q dot. It's because we translate between chemical energy and thermal energy. So it's not about being hidden behind Q dot. And then it says it's implicit in the difference. So that's that one is true. The original equation does not account for the reaction rate. That's not true. So we don't write the reaction rate here, but that doesn't necessarily mean there's anything wrong with that. In fact, we can't write the reaction rate here because it's a conservative property. Energy is conservative. Moles is not conservative. That can change with reaction. Energy is just translated from one to the other. So that doesn't matter. And then the equation is written in the unsteady state. That doesn't matter either. Even if it's written in the unsteady state, it doesn't mean that there's no contribution to energy. So that's the only one that makes sense there. Any questions or comments on any of these? Okay, for this one, we have that our energy, let's see, so this problem has A going to B. And is this a gas phase? This looks like a gas phase reaction. All right, so this is a basic mole balance type problem. So in this case, we want the steady state material balance. So we can work out the steady state version of this equation. So this is written in the most general possible form. So first off, we say if it's a CSTR, RA is the same everywhere. So this term becomes RAV. And then if it's steady state, this is a 0. So we can simplify this equation and write FA naught X equals RAV. So you show all the steps towards that here. I think this is a complete, this is a complete worked out solution. So you can, so that is also shown there. Then we want to know the inlet molar flow rate of A. So it says here the feed is pure A. It's giving us its flow rate and its temperature. And then that's it. We are not even given the molar mass. But we have the reaction here. So if we know the molar mass of B, given that the mass must be conserved in our reaction, then for every 1 mole of B that forms, 2 moles of A must have been consumed. So we can use that to say 2 times the molar mass of A equals the molar mass of B. So the molar mass of A is simply going to be a half this. So the molar mass of A is going to be 24 times 10 to the minus 3 kilograms per mole. So that's the molar mass of A. And then we do have the mass flow rate. So we can divide the mass flow rate of this pure A by the molar mass of A, which we've just found. So it's going to be something like, so it's 12 divided by 24. So it's 0.5 times 10 to the something. So let's just check here. I guess I don't work out the numbers right to the end. So that's the molar flow rate of A. And then what are the inlet and exit molar, volumetric flow rates? So our density is, we need the density in this case. So to get the density, we recognize that if this is a gas, we can simply take, we can say here, if it's a gas, and if the pressure is low enough, then PV equals nRT applies. And then if we multiply both sides by the molar mass, let's see. Well, let's write it out as concentration. So we can say concentration equals moles over volume. And so if we look above here, moles over volume is P over RT, P over RT. So that's concentration. And then to get the mass, we can say mass equals molar mass times concentration. So that's equal to P over RT, or mm times P over RT. So the molar mass times that. So our so that's our mass. Is that mass? This is really density because there's a 1 over cubic meters here. So this is density. So density equals that. Right, so that's density. Now, in the case of the feed, we have pure A, and we've just worked out the molar mass of A, and I think we have the pressure. Do we have the pressure? Temperature of this feed is pure A, temperature. Molar flow rate. So we don't seem to have the pressure and the reaction. Oh, it says here the pressure is 5 atmospheres at all points. Okay, so if we have the pressure, then and we have the temperature. So the temperature is 500 Kelvin. Then that gives us the density. And so we can take the mass flow rate and divide it by the density, and that will give us the volumetric flow rate. So that's what we can do for the entry flow. So the entry flow is quite easy. On the other hand, for the exit flow, it's more complicated because coming out of the reactor is not pure A, it's a mixture of A and B. So your exit flow rate needs to be recalculated, and we'll have to calculate a mean molar density, a mean molar mass. So here is R. So the molar mass, the mean molar mass, we typically write as, so it's going to be 1 over that. Well, let's see that this is if we have the mole fraction, then we can do this. We can just say XA times the molar mass of A plus XE times what is it, kilograms per mole. So yeah, if you multiply the mole, so if that's the number of moles of B, then this is going to be the mass, so that's total mass. And so then that's your overall molar mass. Of course, if you have instead the mass fraction, then it has to be 1 over mm over. So if it's mass fraction, then you have to do this, right? Then you have to get it to a mole basis, and then it's the mass fraction like that. So that's different. Anyway, that's confusing. We don't want to mix that up with conversion. So that's so we have to recalculate the molar mass. Pressure and temperature are the same, so then that gives us the density. The concentration, again, we do need the mean or the total concentration. So for that, we do need the material balance on that whole reactor. And so we need then to write a mole balance on the whole system. So we can say FA equals FA in, or FA naught times 1 minus XA. And then for B, we can say FB equals FA naught. And then we need here theta B, so the inlet molar flow ratio of B. And then we need here nu B over nu new A. So that's the general formula that we derived before. And we realized that we are not feeding any B in. So beta B is simply a 0. And then new B over new A. So new B is a +1 and new A is a -2. So this is a -1/2. In other words, this is 1/2 XA. So it looks like this. And in fact, we could just have looked at the equation and said here that we get half as much B as the amount of A gets consumed. So the amount of A that's consumed is FA0X and then a half that. So then we can say the total number of moles, FT, equals FA plus FB, and that's equal to, so if we just add it, this is FA0 plus, and then it's an FA0 times, and it's a minus XA here, minus XA, and then a plus XA over 2. So this is overall just a minus. So we can write this as 1 plus minus XA over 2. Right, so that's the total number of moles leaving the reactor. So then we can say the concentration C total is equal to, so the concentration at the exit is the total molar flow rate divided by the volumetric flow rate. Right, and that's the thing we are solving for. So that's what we do here. So we've done all these steps. And then if you stick that into your balance here, so here it's PV equals nRT, but instead of V, we are using the volumetric flow rate. And then instead of number of moles, we are using the molar flow rate. So this is the flow rate version of PV equals nRT. And you should always check. It did say 5 atmospheres was the pressure of our reactor. And so if it's 5 atmospheres, that's a low enough pressure. So as long as we are less than 15 atmospheres, we know we can use this. So that's the balance we have now. And then we can work that out as a function of Q. So we can rewrite that in terms of Q. And then, and so we can work out, then we also have FA in over here. So we said that's our molar flow in. And then, let's see, we can then determine. So all of this we had done already. And so I guess that's all ready now. So this is just putting everything together. So we've worked out the flow rate out in terms of conversion. And then we've worked out all the inlet flows previously. And so now if we go back to our original balance, the steady state version of it, then we can just stick in all those quantities here. And even the concentrations can be written in terms of the conversion. And so finally, we have a balance that's purely in terms of the conversion. Everything else is defined, the molar flow in, the temperature and pressure, the volume. So all this is known, and we can just solve this equation for X. So the point of this question is that your flow rate can change. Your volumetric flow rate does depend on your conversion because the density changes as A and B interchange. but you can relate it using your equation of state. And so when you stick it all together, then you get an equation that you can solve for the conversion. Right, so this is a problem that relates to the fact that your volumetric flow rate is changing. So because A and B are changing in a non-equimolar way, so A goes to 2B, I think. So your total number of moles changes. So your flow rate here is not the same as the flow rate there, the volumetric flow rate, it's not the same. So in a gas, the density can change with reaction. And so your volumetric flow rate can change. And that complicates our attempt to write the material balance here. But because we can work out the volumetric flow rate in terms of the conversion, then we can still insert that into our material balance and solve that equation. Okay, any questions or comments there? Okay, then if not, that's it for today. And then let me know if there are any other things you want to go over on Tuesday, and then there's the test on Wednesday.